Today we're going to model op-amps with more than one pole. Before we do that, we're going to review our open loop gain models. When we have open loop gain equals to infinity, that's from your first circuits course. It's ideal and it doesn't change with frequency. Then if the open loop gain is some finite number instead of infinity, you can calculate what the error will be at DC, but still no frequency dependence. Then we have the first model that deals with the frequency dependence, where we set S equal to j omega, and we can use 2 pi gain bandwidth, which is in hertz from the data sheet, divided by S, which can be simplified to the open loop gain as a function of frequency when you're doing Bode plots and frequency instead of radians. Then we have, it's a first order model, but it's not the ideal integrator model, and we have a gain times omega naught, where at DC S would be equal to 0. That would be what you got off of the data sheet, and this would be that very small first pole. You know, sometimes it's just 1 hertz or even 1 radian per second. Alright. Then we have another model where it's a second order model, and here I have omega naught squared, and then I have kind of the extended polynomial format of any generic second order system. Zeta is a damping coefficient that can be greater than or less than 1, and that determines whether it's over, under, or critically damped. Now a sample thing from the homework would just be the AV 1 times 10 to the 6th, and then I've pulled out the 2 real roots. Now let's say we want to determine when will this circuit behave like this ideal transfer function, right? And we have 4 cases. When we're using a finite model, the ideal integrator model, low pass filter model, and a second order model, right? So what this system diagram would be is from V in all the way to V out. We're going to just concentrate from here. We're going to change this from V in to Vx. So first we need to do is find the HS. And so this part here, the summer and HS, is all inside the op-amp. So if you use your equation, V out equals open loop gain times the difference of the input voltages, that means the transfer function of the op-amp is simply AV. If we're using the ideal integrator model, it just becomes AV divided by S. And so really you can right away see that these factors over here just become the transfer function. So let's do an example. When will this behave like a non-inverting amplifier, or when is it actually behaving ideally? So here's we have Vx, so that's all we're worried about. This will behave as a low pass filter as long as lumped element models are valid. So we come in, we have our summer, we go through our transfer function and V out, and then we go through the transfer function and get some back in negatively as we go through beta. So we just write this out, V out equals HS, right, because that's part of the feedback and part of the input, so we pull that out. Then we have Vx of S minus beta V out, that minus because of the negative feedback. We collect the terms and then solve for a new transfer function Qs from here to here, not the HS of the op-amp. And then we get this generic form, HS and beta HS. Now in the book, beta can be a transfer function of itself, and sometimes they'll call it GS. So in this case, GS isn't a function of frequency, it's just beta. So I don't have to rederive this every time. I can just use this system model, identify, oh, HS is this, beta is that, and then just set up my equation and then just plug in various values of HS. So let's do that. We have 4 different cases. The first model, where AV is just a finite number, the transfer equation of that op-amp is just AV, right? No frequency dependence. So we substitute that into QS and we get AV 1 plus beta AV. Well, if beta AV is much greater than 1, then the AVs will cancel. You get 1 over beta, which is 1 over that voltage division, which gives us our classic non-inverting op-amp gain. This can't ring because it doesn't have any memory elements or S terms. That's like a DC equation. Now let's put in where we have the ideal integrator model. Right? That means HS is AV divided by S. Right? And in other examples, I've used 2 pi gain bandwidth for AV. Right? I plug that HS into this equation. Let's turn on the laser pointer. Right? And I get AV S plus beta AV. Now before it was beta AV greater than 1. Now S, right, is j omega, and so as the frequency increases, right, this is going to get as big as this or even bigger. So now instead of it just being bigger than 1, beta AV has to be greater than the magnitude of S. Then QS, if that's true, then we're right back where we came from here, where it's just AV divided by beta. AV cancels, we get our non-inverting gain. This can't ring even though it does have S in this term because it's just first order, right? And ringing is an underdamped response, and you need a minimum of a second order circuit to have ringing. And you might ask yourself, hey, here's a second order part, and here's a first order times a first order. Why can't I have ringing? Because when you gain, when you chain a first order times a first order, sure, you get a second order, but the roots can't become complex. All right, now we'll use our low pass filter model. All right, so we substitute HS for that. All right, I'm leaving out some algebraic steps, and so now this beta AV term has to be much greater than S plus 1, or the magnitude of it. When that happens, QS is 1 over beta, we get our thing. Still can't ring because it's still first order. Now let's use our second order model. We have our gain times the frequency. Here we have 2 distinct real poles, and there's our transfer function. All right, plug that in for HS here and here, and when you multiply everything out, you still have this term, you have this term, and you still have your beta AV, and now there's a 10 to the 6 there. So now it's this. If this whole thing is greater than this, the magnitude of that, will get this gain. Now, yeah, if you have a high gain, beta will be small, right? And your usable frequency range will be reduced. Now, can this ring? Well, it's second order, so it possibly could be an underdamped system, and we'll have ringing. Let's investigate the conditions for that. So is it over, under, or critical? Ring or no ring? So here's our transfer function, and I'm going to put it into standard polynomial format. So I have S squared 1 plus 10 to the 6th. This, of course, is very close to 10 to the 6th, but I put it in this format just so that you can see where did that come from. right, and then 1 times 10 to the 6th, and then we have this term here. So it's all we have to use is the quadratic equation, right, to find out what kind of poles we have. Repeated, real, complex. So A is 1, B is 1 plus 10 to the 6th. It's really 10 to the 6th, right? And then C equals 10 to the 6th plus beta AV 10 to the 6th. So then B squared is this, 4AC is this, and then you just use your standard relationships. If B squared is greater than 4AC, then the roots will be real and distinct. If it's equal to that, the roots will be real and repeated. And if this term is less than this term, we'll have two complex roots, which is underdamped, which can cause ringing. Now, in this case, this AV 10 to the 6 would be the open loop gain that you could get for the data sheet. Coming up with these poles, you can't really get that from the data sheet. Not really. I looked at LT Spice and just started just doing Bode plots and basically identifying the system that they had in there. But here's the thing. The larger the gain, the smaller B. So the smaller beta, right, it reduces this term, and so it'll be more likely not underdamped. But the larger the open loop gain, the more likely it is to ring, because the larger this term, right, could, if it's large enough, be larger than B squared, and you would have ringing. So that's what this second model is from. So really, if you're having an op-amp circuit and you noticed ringing, right, then you have to probably use a second order model to figure out what's going on and come up with a solution for it, right? But this is also why buffers tend to ring, because buffers have the lowest gain. Beta is 1. So that makes this term the biggest. So voltage buffers, it's a real simple circuit. Sure, it's just wiring the output back to the negative input. But you can all of a sudden have an underdamped response where you weren't expecting one. Alright. Now, as we said before, in general, we're trying to avoid that frequency regime where I'm sorry, I'm having a little problem with my pen. That's okay. What I was about to say, I've had other opportunities to say, but if I bring up mdraw, we should be able to. Okay, so what I was trying to say is, as that first integrator model, right, that's the gain bandwidth that you would get from the data sheet, and we try to avoid this area, right, or this is the area we want, so that the circuit will work right. Because in previous examples for looking at the gain of inverting and non-inverting, it comes out and then it gets limited, right? If I have a higher gain, it comes out and it gets limited. Higher gain, it comes out and it gets limited. All right, that's what we've done so far, and that's really with the 2 pi gain bandwidth divided by S model, right? The only, if we don't have an ideal integrator, right, we actually, it does this, right? And this would be the open loop gain from the data sheet, and this would be omega naught, right? And you can come up with that model. But really, the open loop gain at DC is so high that it's acting like DC, and it should work still. When we're looking at the second order model, right, you have this, right, and it comes down, and then you have a a bend. Alright, so that's omega 1, that can be omega 2, and you can come up with the transfer function of that. The thing is that the gain bandwidth is in here, right, and that'll tell you from the data sheet where it's 0, so you can still figure out, yes, I can design in this space. And you might think, well, that pole just, it's so far out of our frequency regime that it doesn't matter. But when you, like, we could have one pole at 1 radian, right, and another pole at 10 gigaradians per second, plus AV, beta, and I'm just going to put 10G here. Then I have AV 10G, and this is the QS, not HS, right? That when I add this part, here was my 2 real roots, but this is adding, making the C of the quadratic equation. This plus 10G is the C. The bigger this is, right, the more likely it'll be underdamped. And beta, right, if it's a buffer, beta's 1, that's as big as it can be. And so you'd have, yeah, the gain would come out, but this would be the actual filter. And yeah, you could, I'm not saying it happens right there, but you could get a Bode plot that looks like that, right? Where we haven't gone over it that much, but a Bode plot that has this peak, has complex roots, and it will have some underdamping. And just so we know that if I have a step function, right, what does ringing really mean, right, is that it does, oh, I think you can see my drawing. That should end it for today.